here, the solenoid that we have, no? So if this is a winding of wire, so if we will try to count the number of windings, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It seems that there are 10 loops or 10 turns, no? And once it is stretched, no, the number of turns of wire, then we can let the current go through the wire, no, in a circular manner. No? So the current there will be spinning something like that. And once it is spinning like something like this, no, if we grab this by our right hand, no, now the fingers of our right hand, since we are using a solenoid now, the fingers of our right hand will now point to the direction of the current. No? And again, no, the way the current behaves here, no, if you will look at it, no, so how does the current behave here? So the current is going up in this direction. No? So let me use this. No? So the current is seemingly going up in that direction. The current is going up in this direction. Okay, so nagalibot ang current natin. Again, no? The fingers there, the 4 fingers represent the direction of the current, while the thumb now represents the direction of the magnetic field. So this end now, the left end of the coil will now become something like a North Pole. No? And the North Pole will probably, no, is where your magnetic life starts and it terminates on the South Pole. But looking at this line is never, no, cut, but it continuously, no, goes roundabout, no, in one circular or rotating manner. No? So nagalibot siya, no, around the coil. No? So again, our right hand rule tells us of the resulting magnetic field whenever there is a current that flows into a coil of wire or into a either into a coil of wire or into a solenoid, no, or straight wire. No? Okay, so here is an illustration also that this coil of wire or solenoid, no, will resemble, no, that of a bar magnet. No? But again, you'll see here that this coil of wire is kind of made closer to each other, and ang nature yan, no? The magnetic field now is going round about our, no, our coil. No? So magnetic field. No? So more on the right hand rule again, depending on the direction of the current. So if it's a straight wire, the thumb is representing the direction of the current, no? I. No? So basta straight wire. But if it's a coil, the thumb there represents the direction of the magnetic field. No? Now, some applications of this right hand rule. No? So maybe now you'll have your motors. No? So magnetic tapes, no? So for some storing of data. MRI, no? Are also some applications of magnetism. No? So we see a lot of motors, no? And loudspeakers also are kind of an application of magnetism. Microphone, no? The pick-up of a guitar, no? The pick-up of an electric guitar. So these are also, no, examples of electromagnetism. They are kind of a microphone, no? Ang pick-up, but in a very tiny manner. No? So it's very, very minute, no? Minute kind of microphone. No? So a buzzer, no? That is a buzzer. Inside the buzzer is actually it is also a kind of a magnet. No? So why does the buzzer keeps on striking, no, a metal? Because again, no, there's a force there that keeps the hammer of the buzzer, no, to strike, no, back and forth the metal there, no, that makes the sound. No? So a buzzer is a kind of a vibrating magnet. No? Now this catapult effect, guys, is a resulting explanation of why motors, no, pushes a wire. No? So again, no, the things that are needed there, no, for us to explain the motor effect, no, of a wire. So if you have here a wire guy, no, And the magnetic field, no, of the wire is or the magnetic field of this magnet, no. So this magnet is called as a U-shaped magnet, no. So the north and south poles of U-shaped magnets are kind of bent, no, and the ends there eventually meet, no. The north and south poles are made to become closer to each other, no, because of the U shape. Another type of magnet that makes the north and south poles come closer to each other are also called the horseshoe magnet, no? So the horseshoe magnets, the north and south poles also are close, no? Now, so if that's the north and this is the south pole, then there must be magnetic lines that starts from the north, no, and eventually ends at the south, no? So north and south pole. So we have here from left to right, no, a magnetic field, no? Now, if there's a wire here, no, so if this one in the middle is a kind of a conductor, a wire, no, and there is current that goes in or out of this wire, no? So imagine this to be going into the screen, no? Or maybe coming out of the screen, no? Now, if this black circle represents the direction of a current, then somehow, no, the current inside the magnetic field, no, on the sides of the magnet here will create now a force, no. Now this force is explained by what we call a principle called left hand rule, no? So if we have a current, no, if this black current is coming from the screen towards me, no? So it's going out of the screen, no? So the black circle here represents a current that is going towards me, no? Now, if I'm going to use three of my fingers, no, in relatively, no, right manner, no? So like this, no? In perpendicular manner, no? So all my three fingers, the thumb, the forefinger, and the center finger, no? Now, if the center finger, which is the longest, no, finger that I have, will be, no, pointing to the direction of the current, no? So the center finger, assuming that the center finger, that's the longest finger. So if that's representing the direction of the current, no, the forefinger representing the magnetic field, no, the direction of the magnetic field, and the thumb, no, thumb, no, represents the thrust or the force, no. So if they are 90 degrees, no, to each other, then you'll notice now again, that these three fingers of mine represents, no, three different effects, no, or three different directions, no. So the current being, no, the one represented by my center finger, if it's coming towards me, no, so I'm going to hold my left hand, no, and the center finger will be pointing towards me. Now the field is from left to right, no, from north to south, no. So if you're going to use your forefinger and point from left to right, no, with your forefinger, the center finger pointing towards you. Now you'll notice that your thumb will be pointing upward, no? So that's using the left hand, no? So if you have your left hand, no, or the left hand rule as they call it, no? Now we will see that the force there, no, the swinging of this wire, no, will be going up, no? It will be going up. So that's what we call a catapult effect, no? So every time you subject a wire with a current, no, to a magnetic field, then once the current is flowing into the wire, then this wire will be thrown upward. So looking at the direction of the force, no? Now again, the left hand rule will probably tell us of this thing we call as the motor effect or the catapult effect, no? So this one will throw the metal. And therefore, again, this one will, if the process here is being made to be repeated and repeated, then you can see a device like a motor to spin. So if there's a continuous force that will cause, no, a continuous force that will make the blades of the electric fan turn, then you'll see a spinning motion on the electric fan. So that's again, the left hand rule. So this is actually the magnet here. There's a wire that carries a current, no? And of course there's a magnetic field here, and then therefore now you'll see the swinging, the actual swinging of the metal. No, once you activate it, no, using a bar, no, a bar magnet. No? This is the left hand rule. No? The center finger, the field, no, for the forefinger, and the motion or the force that goes up. So this is what we call as the left hand rule. No? Okay, do you have a question? So again, this is now the rotating version. So we usually call this as there's a shaft there, no, that causes the rotor to turn, no? But it is subjected, no, by some strong magnets, so that this coil, no, that is passing through the magnet, no, will spin. No? There's a torque that is created in this wire, no? Therefore, if it's a continuous thing, then this torque will create a spinning motion. No? So but you have to subject the wire there, no, with current. So there is a commutator. A commutator is a device that passes the current from the battery to the coils here that is actually spinning. No? So this one, I think the terminals here, no, allows, it's not fixed, no, on the commutator. So there's a device there that allows you to press and continuously contact the commutator. The commutator is the one that is turning there. No? Okay, some loudspeakers and other applications of magnetism. No? Now, most of these are basically, these are actually, magnetic induction. Now, this principle is known as the basic law of magnetism. No? Like poles repel and opposite poles or unlike poles eventually attract. No? So north and south attracts each other. No? So it's never possible that north and north attracts each other. No? Okay, so again, here's a picture of our magnetic field, no? A bar magnet. So the magnetic field there is continuous, no? Actually, that passes into the magnetic wire. No? Okay, so the Earth is one natural magnet, no? So we believe that uh, the Earth now is affected by the compass. So since the compass is magnetic, then our uh, our Earth, no, is also one kind of magnetic material. No? I think no, what they thought of, no, is the core of the Earth is the one that is responsible for this magnetic field. No? Since it is spinning inside, no, it's one whirling, no, molten liquid, no, ang aton outer core, I think, of the Earth. Then that's the reason why there's magnetic field on the Earth, no? And the magnetic field shields us, no, from many harmful rays of the sun. No? So there are other harmful rays of the sun that is shielded by this magnetic field of the Earth. No? Like I think the one that they call as the I think the word there is a storm, no? A solar storm or solar uh, phenomenon. No? So it can destroy a huge part of the Earth. No? So however, no, because of the magnetic of the Earth, it does not reach us. No? Hindi ito malawat. Okay, so we have